So are we good to go? Should we close the doors, I think? Yeah? Yeah, should we close the doors over there? Maybe close the doors. Okay. Okay, I appreciate it. See if you can find a okay. Anyway, thanks for coming to this little seminar. I'm going to be speaking about sort of the connection between surface roughness, surface texture, and friction. And most of you guys already know this, so this is kind of good to, it's almost like a review to see if what I'm saying makes sense. And so any of your feedback I'd greatly appreciate. Some of you in the room, like Ed, has helped me put these charts together over the years. This is the culmination of discussion, basically, with different people in the tribology field and the surface metrology field, and many books that I've read to try and get a picture of how does surface texture actually relate to friction and what's the theories behind it. We all kind of have a notion that, yeah, it matters, but somehow it doesn't always work out maybe the way you think when you start playing around with surface finish to get the kind of effect for friction. So I'm going to talk all about that in the next, what do we have, like an hour and a half, 2 hours, something like that? Hour and a half. And so it's broken up into really 2 modules here. This is a whole class I give, but there's the 2 modules I'm going to speak about are what are called dry friction, so dry sliding friction. And then what happens when you put a lubricant in the system and you have there's sliding friction going on and that kind of thing. So let's just give some credit to all the people that I'm borrowing information from, so I appreciate all their help. And all these books I've read in great detail over and over again. And like I said, I've had a lot of conversation with different people in the field who I will mention as well that help pull all this together. So if you want to dig into this in greater detail, these books are a real good starting point as well. This is a picture that sort of summarizes maybe everybody's general idea when it comes to friction and surface roughness. So what's being plotted is sort of RMS surface roughness on this axis. And on this axis, something we'll call the friction coefficient. And we haven't really defined all that yet, but in the room we kind of have an idea. But the general notion or understanding is that as the surface gets really smooth, so this direction we're going smoother and smoother, we tend to get a high amount of friction. So we all maybe heard of or experienced the idea of 2 very smooth metal surfaces coming together, and as you rub them together, you can get sometimes high friction. Also, we've had situations where you make really 2 rough surfaces, like a brake rotor and a brake pad or something like that, and that can give you quite a large amount of friction. And those are very rough surfaces. And then there's some intermediate range of roughness where actually the friction doesn't depend so much on surface roughness. And many times in my business, that's the kind of situation I'll run into. Clients will come to me with issues related to friction. I'll measure their surfaces, and they've been spending all kinds of time trying to fine-tune their surface roughness, and they're not seeing any effect because they're really just in this kind of sweet spot where it's not going to get any better with surface roughness. You know, there's regions where it just doesn't matter. So this has been kind of the observation. This is actually from one of the books. And this is everyone's kind of experience. The question is, why is this why it is? Why is it why it is? And how can we kind of understand that from a surface texture point of view? So let's first go to some fundamentals. What is friction? After all, this comes right out of Bharat Bhushan's book, which is an excellent book on tribology. I highly recommend. But basically, you can see the definition up there is the resistance to motion, either sliding or rolling, that is experienced when one body rolls or moves tangentially over another. And it's basically a resistive force. So if there's a block and I push on it with some force in this direction, there's going to be some type of force developed that will oppose that motion. And as we know, if I push with some degree of force, it may not move. In other words, the frictional force, which we call static friction in that spot, may be large enough to prevent motion. If I overcome that, then the block will start to slide, but there'll still be some friction, and that'll be kinetic friction. We also have friction related to rolling, too. If we push on some object and it starts to roll, there's also some friction associated with that. We won't talk about that, though, in this unit. So anyway, is friction good or bad? Really, it depends what you're trying to do. Usually people think we want to get rid of friction. Generally true in a valve train, but for someone climbing a mountain, they like to have a lot of friction. And when it comes to a brake, you want kind of some controlled amount of friction. So friction is indeed a design variable in many systems where you got to get a certain amount of friction. And one of the tools we have as engineers is the surface finish at that interface. The history of this field is kind of fascinating, and I'll go through it just a bit. I enjoy talking about it, but as you study the tribology books, and there's a great one out there called The History of Tribology, which again, if you really want to dig into this field, read it cover to cover. It's really good. And they always talk about, well, the first tribologists were like the Egyptians and the slaves, because they found pictures on all these ancient walls of them pouring lubricants underneath these big stone structures they were trying to move, and arguing that man realized if they put some kind of lubricant there, they could get some kind of reduction of this friction. And then the invention of the wheel was also another big discovery, that we could reduce, if we want to drag something on the earth, if we just put some kind of rolling element underneath it, it was a lot less. And then instead of just putting logs underneath the thing, why don't we basically attach the log to the thing and have it roll along with it? That's kind of the idea. Even Aristotle was in this game trying to understand friction. For those that study philosophy, he always talked about things, nothing moving unless you push it. In other words, it's moved by a mover. He didn't really quite understand friction. Later, he realized that there's something going on there. It was Da Vinci that really is credited with some early understanding of friction in an empirical sense. He did a lot of experimentation, and these are some drawings from his notebooks where he realized that if he took a block and he pulled on the block, that the frictional force, the force that resisted his motion, was actually independent of what we call the apparent area of contact. And if I set the block on the wide side or the narrow side, that it didn't seem to matter. And then he also found out that if he increased the load on the block, if he just put a weight on top of that block, the frictional force would increase. And it was generally proportional to that load. And those were sort of the two fundamental observations of basically friction. That was in the 1400s. As history evolved and people talk about the laws of friction being rediscovered or reunderstood, Amitons is credited with kind of bringing it all back to light in a more scientific way. And he considered that friction was coming from surface roughness. So this was the first indication in the literature that this frictional force we're feeling has something to do with interlocking of asperities. So that was kind of the idea, at least in the 1700s. But then we were doing, this is the age of the Enlightenment, and so people started doing real calculating and thinking and realized that, well, if indeed the friction is coming from the interlocking asperities, what would the slopes have to be on the surfaces to get the kind of forces that we're experiencing? And the numbers come out to be pretty big, like 15 degrees. And as we know now, when you measure a surface, particularly a machine surface, slopes aren't that large, they're much smaller, but they weren't measuring surfaces in great detail then. I mean, the microscope was barely invented at that time. Even Coulomb, who we know from electromagnetism, he was involved in the studies of friction as well. And he started postulating that the friction was coming from something he thought was adhesion, plus the roughness, so that he still believed in this kind of interaction of asperities, but that may be something to do with adhesion. And then finally, Desaguliers sort of brought back the idea that friction was coming from adhesion, because he did some simple experiments where he took two polished metal surfaces and kind of stuck them together and showed that there's quite a force holding these two surfaces together, and that's probably where friction is coming from. But then it was a little hard to understand because the theory couldn't explain why the apparent area of contact wouldn't matter. You would think if I had a big, wide, flat, smooth surface on top of a narrow, flat, smooth surface, that the apparent area would matter, and it didn't matter. So there was still a lot of misunderstanding. Also, by this time, people began learning other things in physics, laws of conservation of energy and so forth. And people realized, hey, this asperity business of going up the asperity and down the asperity kind of doesn't hold water, because the energy you lose going up, in principle, you gain coming down. So there was just a lot of confusion. So basically, what do we really know is from the empirical knowledge that the apparent area of contact really has no effect on friction, at least the sort of first order. And if the load or the weight of the object is doubled, its friction would be doubled. And that's kind of all we really know. But what's causing this? And how does surface roughness play into that? And that was kind of the challenge of the times. By the 1800s, we had this great industrial revolution going on, at least in Europe, and people were building trains and stuff. And I like this quote where basically they said, we have no clue about friction, but we just know if we put lubricants on it, it goes away. So by the middle of the 1800s, the early 1900s, as mineral oil was being discovered and basically drilled for, a lot of activity in trying to understand friction kind of went away, because the issue wasn't where's friction coming from, the issue was how do you get lubricant into the interface. Once you've done that, you're done. But that didn't stop the hardcore scientists like Hertz, who began looking at things like contact mechanics and trying to understand when two surfaces touch, what actually is the area of contact. And the real kind of breakthrough came really not too long ago, in the 50s. I mean, to me, that's not long ago. I was around, you know. But basically, there's this famous quote. These two physicists, or electrochemists, I think, is Bowden and Tabor, are really credited with kind of the fathers of tribology and starting the field of tribology. Is this statement here, where Bowden said, putting two solids together is rather like turning Switzerland upside down and standing on Austria. The area of intimate contact will be small. So the idea was, if you really look closely at a surface, and by now in the 50s we had techniques like SEMs and so forth, we realized the surfaces really are composed of these little mountainous structures, summits if you will, and when one surface sits on top of another surface, it's not like it's two absolutely perfect mathematical planes touching. There's a lot of intricacy going on in those touching spots. Also around this time and before, the stylus was invented. So you could actually measure the surface texture and you realize the slopes were nowhere near 15, 20 degrees. So saying friction was coming from these asperities moving up and down each other wasn't consistent. So basically, the 50s is when this stuff started to really come about. And so let me just kind of go back. So basically, their idea is that two surfaces come together. Where they touch is not all that many spots. And where they touch, you get adhesion, and that's where the friction is kind of coming from. And so the friction is coming from the adhesion at these asperities that are touching. But that wasn't necessarily an accepted theory. There was an interesting story. This fellow named Bickerman, Jacob Bickerman, and I'll let you read this if you'd like. I have all the slides and all that, but he basically was in the lab next to Bowden and Tabor working on other things. But when he saw presentations by one of Bowden's students, David Tabor actually, which is kind of interesting, this is when they were proposing the theory of adhesion. He didn't agree with it. He thought that was not good enough. It didn't explain it all. And he was more of a theoretical guy, saying it was more the asperities interacting with each other, banging into each other, going up and over each other, as opposed to adhesion. So this is still to this day a bit of an argument in the tribology field. We rationalize it and we've understood it a lot better now with our numerical modeling, and you'll see all that eventually. But there was a bit of a controversy there, and I actually came across a book. NASA had a big conference on tribology in the early 60s, and he was there as well as Bowden and Tabor and all these guys. And they have the proceedings, and those are discussions, and they were arguing among themselves, even in that time frame, as to where all this is coming from. So let's just review some very basic fundamental material stuff here, because we're going to use some of these results in the equations that we'll find. If I just take a piece of material, put it in a little tensile tester, and start to pull on it, for a small amount of stress, if you will, I'll get like an elastic response. I can pull on an object, let go of it, it'll recover. So if I plot the stress versus the strain, I get sort of a Hooke's law linear relationship. And the slope of that curve is what we call the elastic modulus of the material. I get to a certain point, it starts to yield, then I get plastic deformation. So it still will behave somewhat elastically, but it just has a different slope, and it doesn't return to the original thing until I get to a point where it breaks. Okay? And so the slope of this curve is what we call the Young's modulus, or modulus of elasticity. The point where it begins to yield is the yield strength. And we also talk about the hardness of a material, and the hardness really isn't something you see on one of these curves. It's really related to the deformation of the material. And for metals, typically it's 3 times this yield strength for a metal surface. But let's remember, hardness is really kind of a sort of empirical test. You take a certain denter of a certain size, put a load on it, and find out when it penetrates. Well, here's the deal. Bowden and Tabor said, let's look at this adhesion theory a little bit in greater detail. We know the asperities on the surfaces are much less than 15 degrees. In fact, if you look at a nice ground surface, they're less than a degree surface slopes. And also, clearly have experienced the notion that if you have very smooth surfaces and you bring them together, you can get high friction. So let's just do a basic back-of-the-envelope calculation, which is what I really like about their stuff, is that let's just assume, and I know it's just an assumption at this point, that I bring into contact some surface, and let's, for this sake of argument, make it a perfectly flat and smooth mathematical surface, and I touch an asperity, and the asperity has you know, some material properties about it. Particularly, it has a hardness, it has an elasticity and all that. And let me say that if it just touches one asperity, the minute I put any load on it, that asperity is going to undergo plastic deformation. It's going to crush, right? And the most that it can experience, if you will, the most force it could push up with is basically its hardness times the little cross-sectional area that develops. So hardness is a force per unit area, newtons per meter squared. So whatever little area this develops, it can push back with that many newtons per meter squared times that little area. And the argument is that as I push down this plate, it just comes into contact with many little asperities until the force up equals the force down. So as I push down, I just keep hitting more and more asperities. Each asperity can only push back with a certain number of newtons per meter squared. So newtons per meter squared times that little meter squared that makes up the cross-sectional area. And I support the load that way. So it's just a real simple hand-waving argument. It says, okay, sort of the force down, the W down, equals the real area of contact under plastic deformation, P for plastic deformation, times the hardness. Hardness being typically 3 times the yield strength. So that's basically the whole argument, that I put a plate on a surface, that the real area of contact that develops is just equal to the hardness. It depends on the hardness of the material, okay, and the force that I push down on it. So if I just do a little algebra and just divide both sides of this equation by the apparent area of contact, so the actual size of the plate, right? I'm just doing this to sort of normalize things. So on this side of the equation, I have force per unit area. We call that pressure, if you will, or load. And then on the other side, I have this ratio of the real area of contact to the apparent area of contact. And that should be a little p there too, by the way. And times the hardness. Just kind of invert the equation, you find out something very interesting. That the ratio of the real area of contact under plastic deformation to the apparent area of contact is equal to basically the pressure I push down on, the force per apparent area, if you will, divided by the hardness. In other words, it doesn't depend at all at this point on surface texture at all. You know, nothing in here about surface roughness, RA, any of the crazy parameters we've developed. That you tell me the hardness of the material, tell me what the force per unit area is that I push down on it, and I'll tell you the relative area of contact. In other words, the real true area of contact under plastic deformation divided by the apparent area of contact. And what it is amazing. When you take a material like steel and you just go through the numbers and you put like 200 pounds per square inch. So on a good day, I might weigh 200 pounds. Hasn't been many good days. But anyway, it's like 200 pounds on a square inch. So just a little square inch of steel. If I stood on a square inch of steel on another plate of steel, only 0.05% of that little square inch is actually making contact with the sort of base plate. Very small amount, because steel's hard, so it doesn't take many points, basically, to deform plastically to provide a force up to support the load. And if you go to aluminum or something a little bit softer, okay, it's like 1 or 2%. But the point is, it's very small, that the real area of contact is very small. And so the idea is that this real area of contact is just related to the force per unit area divided by the hardness. And this is kind of neat because it's proportional to the force and it's independent of the apparent area of contact. That's great. It sounds like friction. So their argument was, okay, we've got some simple mechanism here that can basically say the real area of contact is independent of the apparent area of contact, obviously, and it's just basically proportional to the force. Sounds like friction. So the argument is, okay, here's what we're saying, is that the frictional force is coming from, and under the little p for plastic deformation, the real area of contact under plastic deformation times the shear strength of the junctions. So each little junction is formed, and we have some type of little interaction there, adhesion there, if you will. So you take the real area of contact under plastic deformation times the shear strength of the junctions, you've got the friction. And what's kind of amazing is if you look at kind of what it takes to basically shear one piece of metal against another and so forth of the same material, you get friction coefficients of about 0.2. It just sort of works out, which is pretty typical of a steel or a metal surface. So this was kind of a neat, like, wow, this way makes sense. And it didn't take any computers. It didn't take numerical analysis. It took some pretty clever guys sitting. I always envision them sitting over a cup of tea. You know, it's all happening in England. Just basically doing some good physics. So this is great. Basically, we find the friction is proportional to normal force. We find that it's not dependent on the apparent area of contact, and we understand how lubricants work now, because what do lubricants do is they just basically lower the shear strength at the junctions. So we form junctions by plastic deformation. We put lubricants in between those junctions. We lower the shear strength, and we basically have why friction sort of works, right? Basically because we have textures. It doesn't really matter if we have a texture under plastic deformation. We're going to get a certain amount of friction. But that's not the whole story, because as we know and as they knew, not all the contacts are plastic. As you basically polish the surface or just wear a surface in, the asperities get a little broader and broader and broader until they don't crush anymore under load, that they basically deform elastically. So that's a whole other story. And so what about elastic deformation? And clearly, there has been indication that friction does depend on surface roughness. We've experienced it. We know if we make surfaces really smooth, we have high friction. And if we make them really rough, we have high friction. So this model doesn't explain the whole story, but it does explain part of the story. So let's just add to our understanding of strength of materials and just introduce this one parameter, because you'll see it in equations, the Poisson ratio. So basically, if I take a material and stretch it in one direction, it tends to shrink in the other direction. And that amount of shrinkage, that relative shrinkage, is what's called the Poisson ratio. All the other parameters are what we've talked about. All right, so here's where Hertz comes in. Hertz was doing a lot of interesting things in his time, besides electricity and magnetism, it turns out. He's one of the key guys in tribology. And he basically did some realization that if you take two spheres and you bring them together under some force, that there'll be some contact area developing. And also there'll be subsurface stresses and things of that nature, and he calculated those as well. But for our purposes, let's just consider what the area is of interaction between these two spheres that come together. But basically, he found that this real area of contact, and now I put a little e here to mean elastic deformation. So these are spheres, steel spheres. I bring them together, I pull them apart. They respond elastically, is equal to this expression here. It basically depends on the force between them to the 2/3 power, this effective radius of curvature to the 2/3 power, and inversely proportional to this effective modulus. And these effective radii and moduli are kind of defined by here. But this is kind of an interesting result, because it shows that as I bring two, in our world, asperities together, depending upon their radius of curvature, I get a different amount of area of contact between them under elastic deformation. So in words, what this is telling us is that if I have small radii coming together under elastic deformation, think of two pins touching each other, then you kind of have a small area of contact. If on the other hand I have two big balloons coming together, and these are all elastic deformation, then I'll get a large area of contact for the same force. Okay. And also the elastic modulus, which is the stiffness of the material, like a spring, right? The higher the elastic modulus, the smaller the area of contact. Because all that's happening is as I push down on an asperity, in order for it to support me, it has to deflect, right? And develop that area of contact and a force up. If I've got a really stiff material, it doesn't have to deflect as much. And since it doesn't have to deflect as much, the real area of contact it develops is smaller. And indeed, if you look at different materials that are used in certain bearing systems, you kind of get an idea of why they are and the experiences we have. You look at something like a ceramic, a silicon carbide material, the modulus is very, very high there, right? Let's say compared to something like lead or rubber. So if you really want to keep the real area of contact low, you'd kind of go here. If you're trying to increase the real area of contact, you'd go down here, depending upon if you're trying to slide something or seal something or whatever it is you're trying to do. Okay, so where do we go from here is that we're still trying to understand friction from the point of view of surface roughness. And we had a big breakthrough, because in the early 50s they realized, yeah, the real area of contact under plastic deformation actually is independent of surface roughness. And, but we know there's elastic deformation, so what goes on there? We take the Hertz equation, and we know that when I bring two spheres together, I'll get a real area of contact that's dependent upon the radius of curvature of these spheres. That's a good thing, because that's like a surface roughness parameter. And it also depends upon the modulus of elasticity. So a couple people took an attempt in the literature to come up with a simple explanation under even elastic deformation why these laws of friction seem to hold. And so Archert was one of them. He was all part of that crowd in England at the time. And he just said, well, let's just model the surface as a series of little spheres all sitting at the same plane, right? and I touch all those spheres, what happens? Well, you kind of realize that if they're all at the same height, the real area of contact is still going to be proportional to the load and the radius and all that business to the 2/3 power. But we know that the friction is proportional to the load linearly, not to the 2/3 power. So it really wasn't consistent, but it was just a starting point. The huge breakthrough came in '66. Okay, the famous paper, it's known to literature now, is GW66. You see it in every article that tends to reference this. But Greenwood and Williamson in '66 really did the fundamental work, where they said, okay, look, we know surfaces aren't little spheres on planes. Surfaces are more like little spheres randomly distributed. And we know they're more complicated than that. But at least we're going to put statistics in. And let's let the spheres move around. And if we let the spheres move around and say they're randomly distributed, what do I find out? And they did this whole general theory of random distribution of spheres. So they had the more general theory. And said that, hey, if you use an exponential distribution, you actually get an interesting result. You get the result that the real area of contact under elastic deformation is indeed proportional to the load linearly. So it's independent of any kind of exponent here. And it's inversely proportional to the modulus. This sort of stuff makes sense. But here's the fun stuff for surface metrology people. It depends on this effective radius of curvature, or say composite radius, and RMS roughness or deviation of the summit heights. So the first term is sort of like, the larger the force I push down, yeah, the larger the real area of contact is going to be. So I got a bunch of elastically responding spheres. And the stiffer these things are, the less they're going to deform to support the load, so the lower the real area of contact. But here's a nice part. Depending upon the radius of curvature of the summits, I get an effect on the real area of contact. If I have radii that are big and broad, I like to say balloons, surfaces of balloons, then I'll actually have a larger real area of contact than if I have surfaces constructed of little pins and needles. Assuming, again, that they're all deforming elastically. That's the important point. And it's inversely proportional to basically the standard deviation of the peak heights. In other words, how much they're distributed in space in Z. If they're all pretty much in the same plane, and this is a small number, then this becomes a large area of contact. You end up hitting more of these things. If, on the other hand, they're more sort of scattered about, then I actually get a little less area of contact. So this is kind of an interesting result that Greenwood and Williamson came up with, and it works because it basically says the frictional force is proportional to the load. I increase the force, I increase the frictional force because the frictional force is just the real area of contact times the shear strength, and that it has no dependence on apparent area. So this was like another big breakthrough in the whole story. In words, we're just basically saying that friction is the shear strength of the real regions of contact. You know, just whatever those regions of contact is, we get some kind of adhesion or whatever going on at that interface. So if I know the real area of contact and I know what the shear strength is at each of those little junctions, I have an estimate of friction. You increase the force, yeah, sure enough, the real area of contact increases, so the friction increases. You make the material more stiff, a larger elastic modulus for a given force. I get less deformation of the asperities to support the load, so I get lower friction, in other words, a lower area of contact. If I have large summit radii, so big broad balloons, if you will, I'll get a large area of contact. And if I have a rougher kind of surface in this regime, meaning more of a distribution up and down, I'll get actually a smaller area of contact, and I'll get less friction. So this was kind of a nice development, and it's not that long ago, at least in my mind. I mean, I'm almost in high school by then. So it's 1966, right? And we've got this, and this was just published in '66, so it didn't really hit the streets for another year, a few years. Is the laws of frictions all seem to follow, since really all surfaces have texture. So we have these surfaces, they all have these asperities on them, and the fact that the laws of friction, meaning that the friction is basically dependent only on the force to the first power and is independent of the apparent area of contact, is a consequence of the fact that we have these kind of randomly rough, or if you will, distributed surface textures. But here's the interesting thing to visualize, is that as I begin to let's assume I have a perfectly flat plane coming down and it's perfectly mathematically smooth, and I'm touching a bunch of spheres. As I bring that plane down and I start hitting those spheres, what actually happens is that the mean asperity real contact area is actually independent of the force. In other words, as I push down harder and harder, all I do is find more and more asperities in which I'm going to sit on. But the average size, I mean, some will be small, some will be large, but their average size will tend to be independent of the force, which is kind of neat. Also, the pressure that each one pushes back with, and again, I'm under elastic deformation here, is also somewhat independent of the force. That the only thing that's really dependent upon the force is the number of asperities that I'm basically interacting with. And that's where this whole concept's coming from. So as I push down, I get more and more asperities supporting the load. More and more asperities gives me larger real area of contact, so I get a higher friction. But each little asperity is kind of on average the same size, independent of force, and the force each one pushes up is independent of force. The bad news in all this is that, of course, only the exponential law gives the laws of friction. In other words, if you put in other distributions, you don't necessarily get this nice result. And there's also other frictional mechanisms. Clearly, if we have very rough surfaces that are very hard sliding against soft surfaces, they're going to plow through those surfaces. We've seen that. And that'll be a term related to friction as well. And there's also issues about what defines an asperity. Because as you measure the surface roughness and you keep increasing the resolution in which you're measuring it, you keep seeing asperities on top of asperities on top of asperities. So what asperity resolution really matters? So this led to the next question of, when do I know an asperity is going to deform plastically, or as opposed to when will it deform elastically? So this is also in the same paper, the concept of plasticity was developed. So what we're saying is, in a pure elastic mode, the real area of contact goes by this expression. And on a pure plastic mode, the real area of contact goes by that expression, right? So really note that under pure plastic deformation, the real area of contact is independent, really, of the surface roughness. Whereas under elastic deformation, yeah, indeed, the surface roughness matters. Well, what determines whether I'm going to go in which mode or the other? And again, they go through the whole theory there, and they come up with a term called the Plasticity Index. And this is like a simple model for it. As the literature advanced over the years, there's plasticity indices for different types of materials and so forth. But basically, it's a term that looks kind of familiar. It depends upon this effective modulus and now the hardness of the material, and then parameters related to the surface roughness. And let's just look at this. It just says physically, yeah, if you have a really small hardness, that the plasticity number will be large. So basically, a large plasticity number relates to a surface that's going to be plastically deforming. And if you look at sort of the terms related to the radii and the standard deviation of the peak heights, kind of like the roughness, RA of the parts, the smaller the radius, so the more needle-like, if you will, the radii are of those summits, the more likely they're going to crush plastically, right? And it's all consistent with sort of what we probably experience. And so what they definitely showed was that the mode from when you go from a real area of contact under plastic deformation to real area of contact under elastic deformation, that's a very quick function of this plasticity index. And basically, as long as it's like less than 0.6, the plasticity index, that's considered the elastic regime. And if it's greater than 1, we call that the plastic regime. That's kind of the idea. So what happens if I plot the real area of contact as a function of this plasticity term, you kind of see that once you get past 1 or so, the real area of contact is fixed, right? When things are just plastically deforming, for a given load, the real area of contact is fixed. Doesn't depend on surface roughness or anything like that. On the other hand, as you get to a certain regime of roughness, and that's critical how I said that, not just amplitude, not just spacing, but the proper combination, then all of a sudden the real area of contact starts to grow pretty quickly as the plasticity index gets smaller. And this already should start giving us a little bit of a feel for that curve I showed in the beginning, that as you get to smoother and smoother surfaces, smaller and smaller sigma in this equation, that you tend to get a little higher friction. And just to kind of put a picture, and this is what we're talking about. You know, this would be a surface where you can see these are all on the same color scale, and they're just kind of something I doctored up with some measurements I made. But with this kind of surface, you got these kind of sort of more gradual surface slopes, more of a larger radii structures, that this would likely to elastically deform, right? Whereas a surface which has these really sharply pointed structures, you know, real small radii structures, this is a surface that's likely to plastically deform. And that's kind of the idea, all right? Again, just to pull it all together, the idea is that in the elastic mode, the real area of contact does depend on surface roughness. In the plastic mode, it doesn't. This term here, the plasticity index, predicts which way they go. So once you know where you are, the whole question about friction and surface roughness is, how do I relate the surface roughness to the real area of contact? Once I have a handle on the real area of contact, then the argument is simply that of, I take the real area of contact, I multiply by the shear strength at the junctions that are formed, and I have a question of friction. Now the question is, what's that adhesion between these junctions? And that gets into a whole other field that I won't talk about. So here's another picture of just some real data that I've taken over the years in some projects to kind of illustrate this. This was a real world kind of example of an engine component, and it was one of these things where you kind of had the life of the part in front of you, because some regions it didn't wear out, other regions it was looking like it was getting ready to wear out, and other regions it wore out. And when you take it apart, you could see what was happening. In the unworn region, sort of the basic new surfaces that weren't actually run in this one bearing, you know, they actually were on the scale shown here. These are all on the same color scale. It was like what I call rough. And actually, in this case, you might expect that the initial running of this surface, the friction might be kind of high, not because the real area of contact is so large, because in principle it's not, but actually it gets rough enough where you're going to get deformation and side plowing and things of that nature that might effectively reduce the roughness of the surface. And as the part begins to run in, it starts to look something like this, where you basically have plateaued the surface a little bit from running it in. You still have a fair amount of roughness left, and so you're kind of moving along this plasticity curve to maybe you're, just saying at the knee of the curve is kind of where you're at, and that's kind of where you tend to run. And then if things get awry, like you lose lubricants or whatever, and it starts to really polish itself, now the surface gets very smooth, which is what was going on here. And as it gets smoother, you move up on the plasticity curve, and the real area of contact tends to grow. And this is where we start to have seizure issues, where things start to just stick because they're making too much contact. And if the lubricants is not provided, we're in trouble. So this is kind of the evolution of the theory we've been talking about. The actual true model of all this stuff really starts when you think about it with the Abbot Firestone curve, which I know you probably all know about from the field we're in here. But the idea of the Abbot Firestone curve is if you take a surface and just slice it at different levels, you look at the area that you'd be touching. And that's kind of the whole idea. And it turns out that if you're under pure plastic deformation, assuming the density of the material doesn't change, you just plastically deform it, that the real area of contact turns out to be the truncation model of Abbot and Firestone, which is kind of interesting. The Greenwood and Williamson was really the big breakthrough in elastic-only contacts. And then as time went on, other people began to do different kinds of models, Chang, Etienne, and Buji, and so forth. So what's happening now in the literature is with computer programs, we can now really simulate asperities coming together and touching, and we can not only talk about ones touching on top, but side loading and so forth. So we're getting a better understanding of what's going on. But again, the whole idea is to get to that area of contact as like the first order, and then to start talking about other deformation losses that occur as one asperity moves over the other. And again, the work continues on. So what's shown here is kind of interesting graphs of how the different models have been predicting different aspects and coming to, kind of what's observed in the laboratory and so forth. So it's been kind of an interesting kind of story of how friction relates to surface roughness. I mean, you basically, again, come to the idea of if I can calculate the real area of contact, then I got a good handle on it right away. Whatever affects the real area of contact is a good starting point of what's affecting the friction. So I get a way of getting to the real area of contact. I then get an idea of what the shear strength is at those junctions, and I can get an idea of what the friction might be. But bear in mind, there's also losses due to plastic deformation of the asperities, sort of side loading, plowing of one surface to the other. And even when you really dig into friction at the real nano level, we talk about elastic or phonon response. In other words, as one surface slides over another, we're causing lattices to vibrate, and they have hysteresis, and you lose energy that way as well. But that's kind of the notion of this. In the plowing world, there's a term. I mean, you can kind of calculate, and again, Bharat Bhushan does a nice job of it in his book. If you just plow through this surface with even the same materials, with some type of little cutter, if you will, asperity that's shaped like this, you can get an estimate of what the friction coefficient would be as a result of plowing one surface against the other. And it's fairly significant, 0.05, 0.06. So that's truly a mechanism. If the little cutter happens to have a spherical surface to it, then you get an idea of what the radius of curvature has to be in order to do it. So there's certainly a term of friction related to plowing as well. So as you go about trying to solve problems, you got to decide what regime you're in that case. When it comes to the plowing term, I want to add something that's kind of interesting, is that a lot of times we'll deal with interfaces and we'll experience a change in friction, open the parts up, and we don't really see anything exciting. And you got to remember, sometimes debris gets into that interface. And debris, particularly sand particles and things of that nature, could have some pretty steep slopes on them. And those things could actually add to the friction quite a bit. And then, like I say, when you take apart, it's gone. So watch for debris. So the bottom line is, what is the connection between surface texture and friction? Really, first order, it's the adhesion at the real area of contact. That's kind of what we're talking about. There's also deformation of asperities and plowing of harder asperities and so forth. Other parameters also relate to this contact of the surfaces. As we know in the surface metrology world, surfaces aren't just nice random distribution of little spherical capped asperities. There's all kinds of distributions, and we have to be a little bit more aware of that. The parameters we've all studied over the years that we talk about to parameterize surface texture, like RMS, roughness, skewness, kurtosis, all relate to basically aspects of the surface that make them distributed in a non-normal way. So if I have a normally distributed surface, we call a Gaussian surface, yeah, the RMS roughness might be some number like 3, and the skew would be 0, and the kurtosis would be 3. If all of a sudden I plateau the surface and put some dents into it, now the skew gets highly negative, the RMS roughness increases, and the kurtosis gets larger. As a result of this, I'm changing that symmetry. You'd expect I would change the real area of contact. And indeed, that's been demonstrated by some work. Bushanigan, who's one of the fundamental pioneers in this field, basically shows as a function of skewness how the real area of contact changes, and as a function of kurtosis how the real area of contact changes. So different parameters that we've been working with in surface metrology can also be related to the real area of contact. Where I developed along the school of thought of radius of curvature and average roughness, there's other papers that say we can look at just the autocorrelation on the surface or the slope on the surface and relate that to the real area of contact. So there's a lot of models out there. There's not one particular model that we have to use. For the sake of this discussion, you just have to realize that the surface texture relates to friction in first order to how it relates to the real area of contact that's being established. That's kind of what we're after. Bearing area, I mentioned before, is an example of that, where if I look at a profile and I cut through that surface, I look at the area of contact that I would make and I graph that. And then from this bearing area curve, I can get an idea of like how high the peak heights are, how deep the valley depths are, and also just a measure of what's the kind of effective area of contact. So when I look at a surface that might be used inside an engine block, for example, that's a very particularly designed surface, it's usually a cross-hatched honed surface, I get this bearing curve, which is really a plot of the percentage of area that I would bear against as a function of height. So as I wear down on that surface until I get to the right area of contact to support the load, that's where the system will behave. Now, as I mentioned, what's been going on in the literature over the last 30 years has been an explosion of trying to understand surface roughness and how it relates to friction. It's led to a lot of different people doing modeling. So basically, taking actual true three-dimensional surface roughness measurements, putting surfaces together, sliding them against each other, and actually trying to calculate the real area of contact between them. Dong Zhu is one such guy. I happened to meet him in my travels, a real neat guy, and he's helped me make these slides, by the way. I appreciate his help. But this is some of the work he did a few years back with particularly gear teeth. And what's being plotted here is basically if the two gear teeth come together under a certain load, what the area of contact is, and those are those white spots here. Okay. Now I can go a step further in this is basically in his computer modeling. This is a real simple example of a movie he puts together, taking a curved surface and bringing it into a flat surface. And as I bring it in under load, what's going on here is it's basically showing the real area of contact growing and how it would grow for this particular texture. This calculation also assumes, what can go on subsurface. It calculates the stresses and so forth. So I always like to give them some credit. Both Dong Zhu and Jane Wang, they work out of Northwestern University. And they're available for consultation. They have a small company called Tritech Solutions where they actually sell the software that can bring two modeled surfaces together and calculate the area of contact and so forth. It's really kind of exciting things that have developed in this field. So this is a paper a result from a paper that really summarizes all this. I was giving this talk a long time ago, and someone said, "Oh, you got to get this paper. This kind of nets it all down." And I found this paper. It was great. It came out in '92 in the Journal of Physics, and it just kind of summarizes everything we've been talking about nicely. Basically, what they're plotting here is the friction coefficient as a function of sliding distance. So you're sliding one surface over another. And what's going on are the three different curves represent different degrees of roughness, okay? So in the case up here, where you have a high friction coefficient, you kind of see a kind of oscillate, kind of stick-slip kind of thing going on. This is actually the very smooth surfaces sliding against each other, okay? In the case here, where you see the friction coefficient growing, this is kind of a very rough surface sliding against a smooth surface. It's kind of deforming, plastically deforming, maybe digging in, compressing, increasing the real area of contact. And then for some certain optimum surface roughness, the friction coefficient was minimal, and it stayed pretty constant. Now, in this work, what we talk about is basically the correlation length, or kind of like the mean spacing of the surface, as well as its amplitude. And those are the kind of things we as surface designers get to play with, right? You get a certain material property. Now you can maybe tune the nature of the texture to look more like this, if what you want is a stable, minimal friction, and basically get what you need. I'm going to skip through this thing. Basically, friction relates to the adhesion of the surface at points of contact. That's really it. You get an idea from surface texture, relate that to real area of contact, relate that to friction. We also have the idea that friction relates to deformation and plowing, so that term has to be considered as well. The challenge that we all have is choosing the right lateral resolution and height resolution when we study the surfaces we're trying to understand to basically predict or model the degree of friction that we're after. I like to close this part of the talk with this quote from Greenwood I found in some book in '92. He says, "What is clear is that the study of surface roughness continues to get more complicated and that we are a long way from understanding it." I think that's still true to today, actually. So with that understood, basically two surfaces sliding together under dry conditions, and then if we put a lubricant, what happens if we begin to put lubricants into a surface? And that leads us to a whole nother field and a whole nother complicated structure. And in the time that we have, I won't be able to go through in great detail the next slides. The next slides are another hour. I think we have about a half hour, is that right? Yeah, is that fair? All right, we'll push it. We're going to get into the next topic. So let's do that. Where would that be? Uh-oh. There we go. Yep. Uh-oh. Security alert. Doesn't like something. Okay, so what we're going to talk about is now what happens when you put a lubricant in the system. And now you have things that are sliding or rolling, if you will, with lubricant, or in a bearing situation where it's really a sliding thing. We saw this slide before, but I want to make this point that friction is not strictly a property of the material. It's a systems response, okay? In other words, we always kind of think about like the hardness of material or the elastic modulus of the material, and tell me the friction coefficient of the material. That's a no-no, because the friction coefficient really depends on the system that you've actually put this all together. And as I'd like to say, warning, confusion ahead, possible confusion, certainly it was for me. As I began to study lubricated friction, I was having a hard time. The literature was very confusing because they were throwing around the term frictional force and friction coefficient very loosely. And what I mean by that is that if we're just talking about dry sliding surfaces like Leonardo da Vinci played with, yeah, the frictional force was equal to mu, some coefficient of friction times the force, right? That was fine. And you can see that the frictional force is directly related to the frictional coefficient, so they kind of mean the same. One goes up, they both go up, all that kind of stuff. So from this observation of da Vinci, people then just sort of define the friction coefficient as being the frictional force divided by the load. So in the subsequent research that I carried on, as people began to do models and understand friction, they'll come up with some equation for frictional force. They'll have some load in the equation. They'll divide them and say, okay, here's the friction coefficient for this system or this interface. And that's fair to do. But you no longer can make this assumption that it's just this simply related. they may be much more complicated in their relationship. We saw all these before, but basically the idea was people realized that if they put a lubricant on a system, they could lower the friction. They didn't know why, though. They know that, maybe some people are arguing that we know rolling friction is lower than sliding, so that the little lubricant was making little balls. That was one of the arguments. The little balls are rolling. That's where the friction is being reduced. Others just thought that the lubricant filled up the roughness in the surface and made it smooth, so that it decreased the roughness, it decreased the friction. This fellow here, Rene, he said that maybe the surface is being kept apart from each other because of the lubricant. That was an odd thing to think, that you could take some big heavy railroad axle kind of thing and a bearing, and they put a lubricant in there and believe that the two metal surfaces aren't touching, that the lubricant is somehow sticking between those two. But that was the argument, and people began looking at it. Newton, they always kind of claim in the tribology circles, was one of them, but it really isn't true. Newton was worried about planetary motion and hit upon the concept of viscosity, because he was thinking about how planets moved in the universe, and he thought that maybe they were moving through some material, and he had to shear the material, and there was some kind of force associated with the shearing operation. And so he came up with the notion of what we call now viscosity, and basically said that there is some relationship between the shear stress of this fluid and the shear rate of the fluid, and that relationship is, that proportionality is called the viscosity. So I take two planes, I put a fluid between them, I try and move one over the other. The faster I move it and so forth, I experience a resistive force to do that. And that resistive force depends upon, basically, what's interesting is the slope here, the gradient, the change in the velocity over that distance. So that was kind of Newton's contribution to all this stuff, but the history books tell us he really wasn't concerned with friction and wear. Viscosity turns out to be key when we're talking about lubricants. This is kind of the key fundamental thing that saves us, so we have cars that run and so forth. But basically, not all lubricants are nice and Newtonian, as it's called, where you have this simple relationship of shear stress versus shear rate. They behave a lot of different ways, and we deal with it all day long. Ketchup is a classic example of something, I think, what's it called here? Here it is, shear thinning ketchup. So you turn the bottle over, it doesn't move. Once you get it moving, it starts moving quicker. And all these different materials have different kinds of lubricating properties. Just in terms of like what's a typical number for viscosity, it's all set up so water is 1 centipoise, and then the viscosity of syrup is like 6,000, and motor oil kind of goes between 5 and a few thousand, just to kind of give you an idea of the feeling. But again, historically, people were using lubricants since the beginning of time, but they're generally animal or mineral-derived materials. Olive oil, for example, was a big one. But in the 1850s, oil was discovered, and so now, digging out of the earth, people were able to get mineral oil, and now that kind of revolutionized tribology, because now we have these really good lubricants that can do things. The important thing to realize is that the viscosity depends greatly on the temperature of the fluid, and even more importantly, in some cases, the pressure that's exerted between the two plates. And both of these conditions are very critical to making things work, if you will, in an industrial way. Basically, as you increase the temperature, the viscosity drops, and as you increase the pressure between two surfaces, the viscosity increases. We're going to need to know that. Again, historically, a lot of people began working on this problem of trying to understand why lubricants did such a good job. Petrov came up with a simple argument. He said, I know this isn't true, but let's just say I had a simple bearing system. So I have this journal spinning in this bearing shell, and there's a fluid between it. And I'm assuming there's no load on it, which doesn't mean it's very practical, but it's spinning, and that the only source of friction is coming from the shearing of the fluid around that bearing. The metal surfaces aren't actually touching. And he came up with this result that's now known as Petrov's law that showed that this frictional force from just the shearing of the fluid was nicely related to some geometrical factors, but then the viscosity of the material makes sense. The higher the viscosity, the higher friction. The speed, the faster I go, the higher the friction. And the clearance, the narrower that is, the higher the friction. Okay, because you remember the frictional forces depended upon that. So that was kind of like a start in trying to understand it. But it wasn't practical because you put loads on things all the time. Sure, certainly the weight of the journal itself is a load. But the real breakthrough came when, in England, this guy, who I happen to like reading about, I think you pronounce his name, Beauchamp Tower, was kind of like the hands-on lab rat guy. And all the real highbrow physics guys like Rayleigh, they kind of directed him. And they told us, he said, let's go figure this out. So they sent him to the lab to build some test equipment to understand friction. And he realized something that was amazing, and there's a whole story about it. I won't go into it for the sake of time, but he realized that underneath that journal-bearing relationship, that a real high pressure was developing. And he was under the assumption that, they would be touching and that the lubricant was doing something. But from all his calculation, it seemed to imply that there was enough pressure between that journal and that bearing shell to support the load in such that they wouldn't be touching, and that the journals actually were spinning against a fluid surface at all times. And that was like a huge breakthrough. It's like, how could that possibly be? Well, it turns out it can be, as we know, because that's how bearings work, that basically, if you look at kind of the fundamentals of what's going on here, if I slide one surface over the other, I get fluid flow through that interface, and as a result, there's some frictional forces. If I have a pressure difference between a channel, I'll get fluid flow as well and some frictional results. So there's something that goes on, and this kind of describes it the best way. If I just think of two surfaces, one fixed and one sliding over the other, so the bottom surface is down here and it's at an angle, which you always have to have as a constriction, and the top surface is moving parallel to the bottom here, not to this surface. But basically, if you think about it, the moving surface with a fluid in between it is pulling fluid into this interface. So in a given unit of time, it pulls in, if you will, this triangle worth of fluid. And in that same unit of time, the same amount of fluid has to escape out here, or else I don't have a conservation of mass. And if I don't have a conservation of mass, I got problems. So what actually happens is a pressure develops in order to keep this thing balanced, if you will. Pressure develops to kind of push back a little bit on what's trying to be put into the interface and push out what's trying to go out of the interface, get it out of there faster. As a result, a pressure difference develops across that interface, and for practical systems, that pressure can be large enough for a given speed and material viscosity to support the kind of loads that we're talking about. So in order to get these bearings things to work, what we're really doing is playing around with fluid flow. We create a constriction as one thing moves over the other, brings the fluid, and this argument is an incompressible fluid, into that interface. In order for that to balance, if you will, a force has to develop. That force, or a pressure develops, results in a force that supports the loads. So what we're getting to here is the idea that if we can affect the fluid flow through the interface, we can begin to affect something about the load I can carry and some of the frictional effects that are occurred. So Reynolds is the guy that's kind of credited with figuring all this out. Turns out he was apparently working on this stuff at the same time Beecham Tower was doing his stuff, or Beauchamp Tower was doing his stuff. And I found this paper, the original paper from the 1800s or 1900s, and the actual title of this paper was kind of interesting. It was something like a discussion on the lubricating properties of olive oil and some stuff about hydrodynamics, pretty much. Because again, olive oil was the main lubricant of the time. And he just basically derived these basic equations were saying that, yeah, these bearings are working by basically balancing the pressure flow versus the shear flow and all this kind of stuff. And from that, he could derive that there was indeed a force that was supporting the load. The interesting thing to recognize is that the frictional force in these simple little taper bearing things, yeah, it depends on some geometrical factors. Depends on the viscosity. Yeah, higher the viscosity, higher the friction. It depends on the speed, higher the friction, and the area of interaction, the length. The interesting thing, though, is it depends inversely on H2, that little gap there. So the narrower the gap, the higher the friction. We want to keep that in mind, okay? The load that I can support with this kind of a tapered buried system also depends on similar factors, but look at this. It depends on 1 over H2 to the second power. So it's not linear. In other words, if I take the ratio of F over W to get what I'll call a friction coefficient, it actually depends upon H2. So the narrower this gap is, we would say, oh, the smaller H2 is, the lower the friction coefficient is. But unfortunately, in the literature, people say lower the friction is. But no, the friction isn't lower when H2 gets small. Friction actually increases. But the load you can support actually increases quicker than you make it smaller, is the best way to say it. So there's a little bit of confusion in the literature on that spot. So indeed, if you increase the load, you're going to increase the friction. It just doesn't go F equals mu W anymore. It depends a little differently. And this is kind of summarized here in this block of equations, right? That basically the frictional force sort of depends on the square root of W in these lubricated systems, hydrodynamically lubricated systems. All right, well, this is kind of a simple picture of it. When you start to look at circular geometries, it gets way more complicated. I'm going to not even try and describe it, and you can get it all through the books, but let's just hand wave and say the general results are about the same, right? That this clearance between the journal and the bearing shell The clearance is the key thing here. And as you adjust that H min, as it's called, you affect the friction and the load that you can carry, much the same way as we've shown before. All right, so what does this have to do with surface texture? Here's the idea. The key word in the earlier lecture was real area of contact. As the surface texture affects the real area of contact, so does it affect the friction. In the case of lubricated systems, kind of the word we want to watch for is the word flow. As we affect the fluid flow through the interface, so as we will affect the friction at that interface. Unless the asperities are touching, then it's a whole other story. So what we talk about is the idea that there's a fluid film built up between two surfaces, and that minimum film thickness relative to the composite roughness of the two surfaces as defined here, that ratio is what we call the lambda ratio. So the ratio of this minimum separation over the composite RMS roughness. If this is a large number, greater than 3, 4, 6, that kind of thing, then the surfaces are generally really separated. The asperities aren't touching across that interface. And as a result, the friction is really just coming from the shearing of the fluids. As that lambda ratio gets smaller, so basically the either the surface gets smoother, the film gets thinner or the surface gets rougher, then we might get asperity contact across the interface and we get some friction that way. So what we talk in terms of is a relationship or a curve that's known in the tribology literature called the Strybeck curve. And what we're plotting here is this friction coefficient. So remember, it's friction coefficient. For another time, we can talk about the subtle difference between that and plotting frictional force. As a function of basically a parameter that involves the viscosity, the speed, and the load that's exerted between the two components. Let's just think in terms of holding the viscosity and the load the same and just increasing the speed. What happens? As you go faster and faster and faster and you move out to this side of the curve, you basically are entraining more and more fluid and so forth. The film thickness gets larger and you get lambdas much, much greater than 6. So the surface texture has sort of minimal effect at that point on what's going on in terms of the friction. As we move down this curve and we start to slow down, we start to get to a spot where this lambda ratio falls between 3 and 6. And that's called, for certain systems, an elasto-hydrodynamic situation. That's a whole other topic we won't have time for. But the idea being is that they physically aren't touching across the interface, but they're close enough that even under those conditions, we are getting elastic deformation of the asperities from the opposing asperities through the fluid. And that causes an effect on friction and so forth. We get to a point where lambda ratio gets between 1 and 3. Now we actually have asperities touching across the interface. And if we get to the situation where lambda is much less than 1, we get to basically a dry sliding condition if there's no lubricants, and we get a real high friction coefficient. Or if we can at least get some of the lubricants to adhere to the surface, we're in the mode of what's called boundary lubrication. So we're going through these different regimes of lubrication relative to the surface roughness of the surface. And that's kind of the challenge. So this chart sort of summarizes the different regimes and kind of what it physically looks like. I did this real simply in Excel. I took some real surface texture profiles and just changed the lambda ratio, and you can kind of see what it physically looks like, what we're up against. So again, how does surface texture affect this? The sort of pioneering work that was done was in the 70s now, late 70s to early 80s. Two fields of thought, if you will, two competing models. One was by this group in 1970, the other was Petir and Chang in 78. Around that time, these are the guys from Northwestern that ultimately have the lineage to Dong Zhu and Jane Wang. The key point is this, is that if the texture affects the flow of the lubricant through that interface, that affects the pressure that can be generated, that affects the load that can be supported, that affects the way the fluid is shearing through that interface, and that's how you affect the friction. So the key connection between surface texture and friction in a lubricated system, in sort of hydrodynamic lubricated system, is how it's affecting fluid flow. And again, lots of equations and nice math where they basically modified the Reynolds equation and put in terms related to surface texture. But just kind of pictorially, let's look at it. The idea is that if I'm moving this bottom surface relative to the top surface is tilted and so forth. If I have texture in the direction of motion, I call that longitudinal roughness. If I have texture perpendicular, I have transverse roughness. And there's a parameter that defines that, this gamma parameter. If it's defined to be infinity in longitudinal roughness, it's 0 in transverse roughness. And there's a simple way of calculating this based on autocorrelation functions. But this is pictorially what we're getting at. In the case of longitudinal roughness, where the asperities are aligned in such a way that you have flow in the direction of motion, yeah, you get an augmentation of the flow, okay? And if you have transverse roughness, you get a diminishment of the flow through that interface. And if you have some isotropic roughness, you have something in the middle of that. So as a result, we get this pressure flow factor that develops as a function of this lambda ratio, H over sigma. If the lambda ratio is real large, then the surface texture doesn't matter too much. So if you've got a thick enough film, certainly the surface texture doesn't matter, thick enough relative to the RMS roughness of the two surfaces. As that lambda ratio starts to approach 3, yeah, it definitely matters. And as you get to 2 and 1, it's a pretty significant effect. So in the case of like when you're getting close, 2 or 1, and you have transverse or longitudinal roughness, you get a lot of extra flow through that interface. If you have transverse roughness, you kind of get flow being occluded. Here's basically a quick little summary from the work from Christensen in the 70s. You just kind of look through this table. It kind of shows you what you might think might happen from a physical point of view. Just as a typical example, if I have a nice clean bearing system and then I all of a sudden introduce transverse roughness to the sliding interface, well, that's going to prevent fluid flow. So if I'm going to prevent fluid flow, just like putting a small gap in there, I'm going to have to build up a higher pressure to balance that system. So as a result, with transverse roughness, I actually can support a little more of a load. I'll be able to develop a higher pressure to support higher load. But at the cost of increasing the friction as that fluid shears over those texture features. That's kind of the argument. Again, all the modeling that they did just demonstrates things like how the load you can support varies with the lambda ratio depending upon the geometry of the bearing. So, for example, if you have a very narrow bearing, the results are just the opposite, because now you got to consider side leakage as well. So now fluid leaks out the side, you got a problem. So you can see how complicated it gets rather quickly. Also, whether you're moving a smooth surface against a rough surface or vice versa, you also have some effects on the friction. In one case, you're basically pulling fluid against surface roughness features, so you kind of get an increase or decrease in flow. Where in the other case, the surface texture is on the moving surface, it's sort of carrying the fluid through the interface, so you get an increase in flow. So those are some of the arguments and some of the results. Again, for the sake of time, I won't go through all that. I won't be able to cover EHD, but I want to just get to a kind of summary chart. We talked about the modeling that's going on and the same kind of thing that the modeling Dongzhu and his group has been doing. They can model fluid surfaces and calculate things like the fluid film buildup, the pressure, and so forth. This should be, I don't know if the model's going to be running at this point. But anyway, that can be done. What's happened now, which is exciting in this field, is, again, just to summarize here, when it comes to dry sliding friction, it's a real area of contact that counts. And then the asperities that make what the shear strength is of those junctions. When you have fluids involved in a hydrodynamic or quasi-hydrodynamic state, we're worried about fluid flow through the interface and how surface texture affects that. So once people have understood this, a lot of neat research has been going on over the last 10, 15 years where we're texturizing surfaces on purpose, right? We're creating very deterministic structures by laser etching and so forth, the surface finish, to produce little asperities or little pockets that create some of these hydrodynamic lift areas. And this is just one paper showing as a function of speed how they're affecting friction coefficient with these different textures as it goes and orientation. This chart in this one is the way I like to kind of summarize this whole presentation in the last 90 minutes. This paper came out not too long ago, 07, 08, and it was really quite nice. The paper was talking about a new tribometer system that was developed for measuring friction and so forth. But what these authors did was basically do a study where they were sliding on a disk like a ball surface. Ball wasn't rolling, it was just sliding. And they were plotting as a function of time, which is nothing more than the speed, so they're increasing the speed, the friction coefficient for different roughness values of, say, the ball. I think it was the ball, the base surface. But the idea was really kind of interesting. It basically showed that, over here at real low speeds, that the friction coefficient was somewhat independent of surface roughness. Okay? As they increase the speed, which is what this axis is, yeah, the friction coefficient begins to drop for all of them. It drops the most for the lower roughness part. This is an RA of 0.04. It drops, but not as quickly for the higher roughness part, RA 1.6. And as we go faster and faster and faster with this lubricated system, we're entraining more lubricant, that you can see that it looks like all these curves are going to basically come together and converge at a point, because they're basically, after you go fast enough and the fluid film gets thicker, the surface roughness doesn't matter at all. So this chart, when I read this paper, is that this is the whole presentation I've been giving summarized in one graph, because basically what it's showing is, yeah, at real low speeds, where you don't have lubricant forming an actual film that's supporting the load, you have asperities touching, that you're basically back to the old plastic deformation model. And for these materials, it's all plastic deformation. So the real area of contact here at real low speeds is independent of surface roughness. Okay? As you begin to entrain the fluid, as you're going faster and faster, yeah, indeed, the lower roughness parts are going to have a larger lambda ratio for a given speed. And so their friction is going to drop quicker than the other ones. And as you go fast enough, the film thickness gets so large that all the lambda ratios are much greater than 5 or 6. And so the surface roughness really begins not to matter as you go out into that speed. So you can see this nice, basically summary of all the things we've talked about, and that at real low speeds, with lubricant or without, you got plastic deformation. The real area of contact develops. It's somewhat independent of roughness at that point, and so the friction is pretty much stable. Same for all roughnesses. As you begin to get that interface going, yeah, the friction drops quicker for the lower roughness parts. As the interface gets faster and faster, then the film builds up. It's thick enough to where the surface roughness begins to not matter as well at that point. And that's basically the challenge that we all have to do. And as a result of that, there's been a lot of papers where people are playing around with different kinds of surface textures, surface geometries, in order to affect fluid flow through the interface. So the final thought here is this: the understanding of the interface is really related to the flow and the factors that affect the flow. That's really what we're getting at with surface roughness. The film thickness and the viscosity relate to the ultimate friction. That's kind of where we're at. Because we're assuming in a nicely lubricated system, the asperities aren't actually touching anymore. It's basically the shearing of the fluids and that related that. As the interface goes mixed and you get asperity contact, then we start to move back into the dry sliding mechanisms of just real area of contact deformation and plowing. So you net it all down right here. How does texture affect the lubricated system? First, it's all about flow. Then it's all about shear. Then it's all about real area of contact. And then there's arguments that you want reservoirs of surface texture to hold fluid, so when the interface stops sliding, you at least keep a lubricant in the area. And that's how surface texture is kind of played in this field. So that's basically the story of roughness and surface texture. Any questions at this point? Yes?
Not really a question. I wasn't familiar with that last paper. It was interesting. I noticed there's medium, the smoothest surface.
Oh, this one here?
Up to the next roughest one.
Yeah, this was a great paper.
20.
Yeah.
And then the next surface up only a factor of 2.
Exactly, yeah.
Yeah, so they have a really smooth surface.
Exactly, yeah. It's a very, very significant paper, I think.
Yeah, really smooth, pretty darn rough, and even rougher.
Exactly, right. And what was well, I'll tell you what was exciting about this paper. When I saw it, and when I was doing all this over the few years, and I go, I think that's what I wanted to see, And the authors didn't understand this. It was the first time I ever wrote back to one of the authors. One of the authors was the boss of this guy here. That's Yuchang Wang. And I wrote back to him. I said, I think I know what's going on. I go, this is all plastic deformation, just real area contact stuff. Because they said in their paper it's a little confusing why it doesn't matter. I don't know if that ever got published, but that's clearly what's going on. It makes total sense. I said, great. So that made a lot of sense, yeah. So I should say, I'd like to point out, I hope you're not embarrassed, we have tribology legends sitting in the room right here. This guy, Ed Becker, I hope you don't mind. If I mentioned Bowden and Tabor, they were kind of the key guys. And one of their graduate students was a guy named Ken Ludema, who was a professor at University of Michigan. Ken Ludema was also the graduate student of Abbot and Firestone, who did the basic Abbott Firestone curve, and also are credited with inventing the stylus. And Ed is a graduate student of Ken Ludema. So I think that's always cool. I always embarrass him whenever he's in the room. I think it's kind of cool anyway, that this field is that new, that we've got dignitaries here. Any other question? What's traceable? Traceable. I got a traceable standard. Traceable to the original tribology guys. I think that's kind of cool. I think it's neat anyway. All right. What else? Any other questions? Okay. I guess that's it. Okay. Thanks.